Okay, good afternoon, everyone. Let's start it. So first of all, address the TA office for the Tuesday, so that we're gonna change the office hour from to the 9:30 to like 11. It's not like the previous time, because for the previous time slot, we don't have any available physical space for the office hour. Right now we have. I will post the change in the Canvas shortly, and also update to the course website so that we now guarantee like for every weekday we have a office hour, physical office hour. So please take advantage of those office hours and let us help you. Okay. So let us continue with the, a second, by the way, please start considering what kind of projects you want to do. You either want to do some paper reading, deepen understanding for some frontier research, or you want to do some real world problem, right? Project. So please start considering that. If you want to do the project, research project, you can consider team up with somebody else, right? And we'll soon ask you guys to submit your decision. Okay. So any questions so far? Yeah. Homework 1. It will be released on Thursday, because for homework 1, it will be covering all the basic probability distributions and properties we have discussed so far. So that's quite a few like probability distributions that we need to go through. So we need some time, and also ask you to practice some problems like show, for example, show some problem, which is help you to deepen your understanding about those fundamental properties. But don't worry, those properties have already been discussed in the class. Other question? Okay, great. So let us continue with the basic or very important probability distributions that form our basic building blocks of probability models. Right? So in the last lecture, we talked about binary variables, right? Binary variable means that your random variable is either 1 or 0. So it's very natural that we're gonna assign a Bernoulli distribution, right, to represent or to describe the distribution for binary variable. So the density, suppose some x, right? X is either 0 or 1, right? Follows a Bernoulli distribution, then its probability density can be written as x to the power of mu to the power of x times 1 minus mu to the power of 1 minus x, right? So if we take the value of x to be 1, then the probability is mu. If x is 0, then the probability is 1 minus mu. It's very natural and intuitive. Now, let us extend this to the general discrete random variables, which we call categorical variables. Suppose you got a random variable. It can take big K values, right? K is no less than 2. That means if K is 2, that means it's just a binary variable, right? 0, 1. Right? But if K is 3 or 4, then it represents multiple classes, right? 0, 1, 2, 3, 4, up to whatever number of classes you want. Right? This is very, very common in practice. For example, image classification. Right? You want to classify if your image contains a list of animals, right? Cat, dog, rats, and all kinds of other stuff, right? So this is a typical multi-class problem. So we do need some kind of probability distribution that can describe the categorical variables, right? So first, we're going to use a k-dimensional vector with only one non-zero entry to represent a sample of categorical variable, right? So I know that like at the first sight, you want to say, okay, now that x is categorical, then I can take x to be 1, 2, 3, no, let's start from 0, right? 0, 1, 2, 3, something like that, right? This might be the most intuitive way to represent the value that a categorical variable can take. Okay? However, when we handle the machine learning problem, we instead represent X as a vector, a k-dimensional vector. Like suppose we have k possible values that X can take. And in this vector, there will only be one element that can take value 1. All the other elements are simply 0. So suppose if we take k equals to 4, meaning that, okay, my random variable can take 0, 1, 2, 3, right? Take 4 distinct values. I'm going to represent X with a 4-dimensional vector. In this 4-dimensional vector, there's only one entry that can take 1. Now all the other entries take value 0. And the entry that takes non-zero value, meaning 1, represents the particular category that X takes. So we see here, right? If we observe that X takes category 2, that means its second element is said to be 1, and all the remaining elements is said to be 0. If I want to take category 3, then my X representation will be 0, 0, 1, 0. If 4, it will be 0, 0, 0, 1. Okay. So this is called one-hot encoding. Does it make sense? Right. So we'll see in a minute why we would like to represent a categorical variable in this way, because it will be very convenient when you do maximum likelihood estimation and all kinds of stuff. So any questions so far? Everyone's comfortable, right? Okay. So then how can we write down the probability distribution or probability density of a categorical variable? It's very similar to the binary variable case. But right now, because we have k possible values, right? K possible categories, then this distribution will be parameterized by a probability vector, right? So we denote by mu, both in the mu, right? Mu1, mu2 to mu big K. So mu1 represents, okay, the chance that X takes the first category. Mu2 represents the chance that X takes the second category, and so on. Right? Then we can represent the probability of a specific instance of X as a product from 1 to big K, where we multiply each chance mu k to the power of the kth element in Xt. Why is this correct? Anyone tell me why is? Yes, exactly, right? So as we just mentioned, right, we represent X as a one-hot encoding, meaning that in this vector, all the elements are 0 except the value you really take, the category you really take will be said to be 1, right? So that means if I write down this probability, it will be just mu k, the corresponding probability, right? So if we write it in this way, we kind of like unify whatever cases you choose, right? It can represent the probability you take category 1, 2, 3, 4, and so on, right? Take one particular example, like for example, if I take specific category, say x1 equals to 1, right? That means all the other x elements will be 0. So then you can imagine in this product, for all the k's whose value is not 1, sk will simply be 0, right? then you take the power of 0 is simply 1, right? So only with the k that corresponds to 1, you have the mu k, right? You have the right probability, right? Because the power is simply 1. Does it make sense? This is a generalization of the representation of binary variable distribution. And also we need to be careful because it is parameterized by this probability vector. So that means each element in this mu vector will be non-negative because you don't have negative probability, right? And also their summation must be 1. Does it make sense? Any questions so far? Okay. So now let us consider, given the data, how do we estimate this probability vector mu, right? So suppose we have n ID observations x1 to xn. So remember, each xn is a one-hot encoding, right? So we can write down their joint probability as a product over all the examples. For each example n, the probability is a product over all the classes k, right? And for each class k, you got mu k to the power of x and k. So x and k is actually the kth element in the example xn. Okay. So we can simply merge them, right? Because for the mu k, it shares the power from every corresponding observed sample, right? Sample. That is x1k, x2k, x3k until x bigger than k, right? So there's a summation here. So you can represent mk as the summation over all the examples where the summand is the kth element of every example xn. And then we want to estimate mu, right? Suppose we want to use maximum likelihood estimation. So we can take a logarithm, and then this is our log likelihood, right? Just from here, you take logarithm. The product becomes the summation. And here we should consider the constraint that the summation of all mu k's will be 1, right? So we need to add a Lagrange multiplier. Does it make sense? Then the remaining step will be just take the gradient with respect to each mu k and set the gradient to be 0. And you see that the maximal likelihood estimation of each mu k is simply mk over n. So mk is what? Mk is actually the total number of the appearance that class k shows up in the data, right? And over n is total number of examples. It's actually the ratio of each category k observed in data. Does it make sense? Yeah, if you feel like a little bit difficult to catch up, doesn't matter, because after that you can just spend 1 minute to derive it yourself. It is like classical result. Okay. So similar to binomial distribution, right? So we can extend the categorical distribution to the multinomial distribution. So what does the multinomial distribution mean, right? So consider that okay, you're still like doing some random experiments, right? But each random experiment, the outcome will have multiple classes. Like you're rolling a die, right? You got 6 points. That means you have 6 possible values, and this multi-class problem, right? And then suppose you rolling a die for big N times, right? So what if I would like to know, okay, I observe the probability that I observed point 1 has been observed for 10 times, point 2 has been observed for 20 times, point 3 has been observed for 23 times, and so on. And then this probability follows the so-called multinomial distribution. So here M the M vector represents the count of each category is observed during your big N experiments. Then we can write down the probability of your M vector, that is actually count vector of those categories, as a combinatorial number, which means that, okay, out of like N experiments, which particular you have observed M1 times for categorical 1, M2 times for categorical 2, until MK, big K times for categorical K. How many possible combinations out of from this big N experiments times for each particular such experimental result, what is the specific probability, which is simply a multinomial, simply a categorical probability, right? And this is what's the definition of this combinatorial number, right? Okay, any questions so far? Is there everyone comfortable with this? I assume that you guys have already known this before. Okay. So now we want to briefly mention that how this categorical distribution is leveraged in probabilistic modeling of general machine learning, right? So as we mentioned, right, that categorical distributions or binary variables distributions they're often used to classify things, right? I want to classify what type of images according to the pixel values of image, right? I want to classify the topics of the document according to the words, right? So in practice, when we leverage machine learning models, right, we want to build up such a classification models, right? The key is to parameterize or model those parameters mu or mu vector with some kind of model according to the data. For example, you got image, right? You got a image pixel values, right? I want to use these pixel values to model a categorical distribution, which can tell what is likelihood that this image belongs to class 1, this image belongs to class 2, this image belongs to class 3, and so on. So then, in essence, those models all kind of like model the parameters of these categorical distributions in whatever forms you want, right? For example, a very commonly used form is to introduce some linear model. For example, this alpha will be some feature vector. It might correspond to the pixel values of the image or correspond to the words in a document or correspond to whatever other feature vectors in your data. Then we're gonna use a linear transformation of those feature vector and throw them and then put them into some transformation to get some valid probability. Say if we want to do the binary classification, we know that this probability must be a valid probability, right? That's between 0 and 1. So I put a sigmoid transformation so so it can give me a valid probability, right? If we want to do another is that, okay, I put this linear transformation of the feature vector into a cumulative density function of Gaussian distribution. So it will also give you a number between 0 and 1. So you can treat it as a probability. If you want to do the multi-class classification, you can take exponential of this linear transformation according to different vector, and then I normalize. Then this mu case, mu1 to mu2 to mu big K, they will form a valid probability vector, right? Because they all are non-negative and their summation is 1. Then once I parameterize those probability vectors or just probability for binary variable, and then I just fit data, right? I just fit data, I estimate those parameters like W or WKs to best fit the data. That's the key idea. And we'll get into that in more detail when we talk about specific models. But any questions so far? It's not same mu. So here, this mu, without any subscript, it just represent the parameter for Bernoulli distribution. For the Bernoulli distribution, your outcomes only 0 or 1, right? So only need one parameter. But when we talk about mu k, is actually talking about we're actually talking about the general categorical distribution. We got mu1, mu2, mu3, and so on, represents the probability that it takes the first category, second category, third category, and so on. And then we just, I mean, whichever case, like if you want to do the binary classification, you're gonna, you only need to model mu, right? You only model mu with some feature vector. But if you want to do the multi-class classification, you have to model the mu vector. Right? Each of these elements is mu vector. You have to model them according to your feature vector. Does it make sense? Any other question? Okay, great. So now we have tools to model discrete observations, right? Either binary observations or multi-class observations, right? So now let us consider what if I want to assign some distribution over the parameters of those discrete distributions. Say we got a Bernoulli distribution, right? So we know that this x is either 0 or 1, right? And this Bernoulli distribution is determined by this mu parameter, right? So its probability density is mu to the power of x times 1 minus mu to the power of 1 minus x, right? Then the question is that, what if I want to further assign a distribution over mu? Remember, mu here is a probability. It's a negative, it's between 0 and 1. So this probability distribution must naturally satisfy this probability, right? You cannot sample a negative mu, right? A negative mu won't be able to parameterize a valid Bernoulli distribution. Right? So a very commonly used distribution over mu is called beta distribution. So the beta distribution, the support of this distribution, meaning that all possible values that the mu can take is between 0 and 1. And this is the density of the beta distribution. And here, the gamma here is called gamma function. So you can view it as a generalized version of the factorial. So if A, say for gamma A, right, the input is A can be continuous, it can be integers, right? If A is integers, then gamma A is just the factorial of A minus 1. But A can also take continuous values. Okay? And there's some nice properties of this gamma function, that is gamma 1 equals to 1, and gamma A equals to A minus 1 times gamma 1, gamma A minus 1. Okay? But we don't need to really understand the details about gamma function, but just be aware that there's a gamma function in the density of beta distribution and use it by default. So here is the shape of the density of the beta distribution. We choose different parameters. Like so, beta distribution is parameterized by two values, A and B. Right? So different choice of A and B will lead to different shape of the density curves. Like if you choose A and B equals to 0.1, you can see that the density that mu takes value close to 0 and close to 1 is much higher than you take mu to be in between, right? To be in the middle. But if you take both A and B equals to 1, you can see that actually it is deteriorates to the to the uniform distribution. Right? And also, if you take unequal values for A and B, you give like different shapes of the beta distribution. So beta distribution, here are like another two important properties of the beta distribution. So the expectation of mu is A over A plus B, and the variance of mu is like this. Again, you don't need to memorize this. Once we need to use that, you just look up the dictionary. So why do we use beta distribution? Beta distribution is the conjugate prior to the Bernoulli likelihood. So later we'll discuss what is conjugate prior. But basically, it means that, okay, if you model your data with Bernoulli likelihood, and if you assign beta distribution, beta prior distribution over those mu values, then you can directly compute the exact form of the posterior distribution. You don't need any approximation. So that is called conjugate prior. That's why beta distribution is popular. It's not because it has a like very big rationale that you must assign such a prior probability. You can construct other prior probability, prior distribution over some non-negative number between 0 and 1. But if you use beta distribution, it will make your computation much more convenient. We'll get to that later. So now let us consider the discrete distributions, right? So we know that in general, like if we have a big K possible values, right? So we can parameterize the probability density for categorical variable with categorical distribution. Right? So a natural question will be, okay, can we also assign a prior distribution over this probability vector that parameterize a categorical distribution? So this distribution is called a Dirichlet distribution. So basically, you can imagine that the Dirichlet distribution will sample a probability vector, a valid probability vector, meaning that every element is between 0 and 1, and their summation is 1. And this probability vector can be used to parameterize a categorical distribution. Does it make sense? Right. So this is a form of a Dirichlet distribution. So it is parameterized by a alpha vector of the same dimension with mu. So your mu vector contains k possible values, then your alpha vector contains k values as well. And each element in this alpha vector is positive, and this alpha vector is called concentration parameters. And the density of the Dirichlet distribution has the following form, right? So in the product form, inside each product goes from k equals to 1 to big K, and each term is mu k to the power of R of k minus 1. Okay. So it's kind of similar to the categorical distribution, right? So for the categorical distribution is mu k to the power of xk, right? Xk is the kth element in the observed categorical variable, right? But here, the power is R of k minus 1. Okay? And then this guy is the normalization factor, right? So the denominator is a gamma function of the summation of all the concentration parameters here. And numerator, and denominator is a product of the gamma function over each concentration parameter. Okay. Again, you don't need to memorize that. I just introduce the structure of the density function. In future, if you need it, just look up dictionary. And from geometry point of view, like Dirichlet distribution essentially is to sample points on simplexes. Right? So simplex is you can view it as kind of like a linear manifold, but in the three-dimensional space, it's just a plane. Right? And every point in this plane represents a probability vector, meaning that every point every element in this point is non-negative, their summation is 1. Right? So that's why people also say, okay, Dirichlet distribution is distribution over simplexes. Right? And we can also view beta distribution as a special case of the Dirichlet distribution. And when you set big K equals to 2, right? So this density will become exactly the same as the beta distribution density. Any questions so far? And here are some nice property of Dirichlet distribution. So the expectation of mu k, so remember mu k here is a probability, right? It's between 0 and 1. Is the alpha k over the summation of all the alpha k's. Okay? And we also have like expectation of logarithm of mu k, which is computed by this psi function of alpha k, subtracted by psi function of the summation of all the alpha k's. So the psi function is called digamma function. So it's a derivative of the log gamma function. But again, you don't need to memorize this. Just give just have some impression that why we introduce this, because later, probably in the middle of this semester, we talk about the topic models, the classical topic models. When we use variational inference, where put those directly distributed random variables, we'll need to compute some expectation that will include the expectation of log mu k's. Any questions so far? The training would amount to like estimating those alpha k's, right? So it's concentration parameters. And but here we haven't started talking about how to train them, because when we talk about here, like we talk about, okay, if I want to assign the prior distribution over parameters for categorical distribution, right? And then given the parameters of categorical distribution, we can model the observed categorical values. So you can see that there's hierarchy. There's hierarchy on this probabilistic model. And then during the inference or during the training procedure, you might want to estimate both the values of those categorical variables probabilities and those alpha k values, or you just want to estimate part of them. Right? That depends on your need. So we'll talk about them in a more united framework later. Other question? Okay, great. So again, why do we specifically introduce Dirichlet distribution, right? Do we have any other distributions that can assign a prior over a probability vector? The answer is yes. But here, the major reason is that we emphasize this, is that the Dirichlet distribution is a conjugate prior to the categorical likelihood. That means if you want to use categorical likelihood to model some discrete observations, then you assign some Dirichlet prior over the parameters of the categorical likelihood, then your posterior distribution can be computed exactly. You don't need any approximation. Okay. Again, we're going to emphasize this when we talk about what does it mean for conjugate prior. So here we just want to briefly mention that this model is called latent Dirichlet allocation. So this is very, very hot research topic about 15 years ago when I was doing my PhD. This is like a mainstream topic in machine learning. Although right now people are not too many people are focused on this topic, but this model is built upon the so-called Dirichlet distribution. And the goal is to automatically extract topics from documents, collection of documents, and also extract the words that represents documents. the idea is that, okay, I'm gonna will those words, like, the different words as different class, right? So the whole document can be viewed as many multi-class predictions. And then each topic can represent this different categorical distribution, right? And then naturally we will assign a prior probability distribution over the probabilities of those words. So they use the Dirichlet distribution. Then the whole model is about, like, the whole work is about how to automatically infer the posterior distribution of those word distributions according to the data. We're gonna go through the details of this latent Dirichlet allocation model later. But here, just to give you a sense. Okay, so far we have covered like discrete observations, right? Binary observations or multi-class observations. We have Bernoulli distribution. We have a categorical distribution. Also, we know that, okay, how do we further assign a prior distribution over the parameters of all those discrete distributions, right? So next, we're going to talk about what if you have continuous observations, you have continuous random variables. Then what kind of distribution is very useful to characterize those kind of those type of values, right? Obviously, the most commonly used continuous variable distribution is Gaussian distribution, right? So everyone knows in the single scalar case for Gaussian distribution, we know it is parameterized by the mean mu and by the variance sigma squared, and its probability density can be written this way, right? So it is exponential to the power of minus 1/2 sigma squared and x minus mu squared, right? And this guy is the normalization factor, right? It is to ensure that if you integrate the probability density with respect to x, it gives 1. Right? But our major focus will not be single variable case, right? Our major focus is a multivariate Gaussian distribution, and this is extremely important for probabilistic learning. So in general, if your random variable is actually a random vector, like it's k-dimensional, for example, right? So we say x follows a multivariate Gaussian distribution, means that it is parameterized by the mean vector mu and the covariance matrix. Right? Suppose x is k-dimensional, then the sigma is k by k. Right? Of course, this mu vector will be k by 1, right? And this covariance matrix is positive definite. Right? And here is the probability density of this multivariate Gaussian distribution. It has a nice and clean form. We can first take a look at the exponential term, right? So the power of this exponential term is minus half times the quadratic form. Right? It's x minus mu transpose sigma inverse x minus mu. As mentioned before, right? This quadratic term can be written as a trace, right? Because you take a trace of scalar, is still that scalar. So we'll take the trace for that. We mentioned that you can rotate the matrices and vectors inside the trace, right? You can move x minus mu to the leftmost. So it can be also written as a trace of x minus mu transpose, and sigma inverse. And this guy, 2 pi sigma, the determinant of 2 pi sigma to the power of minus half, obviously serves as the normalization constant, right? So sometimes people feel like, okay, why should I like memorize a big sigma matrix and then take inverse from like compute this density, right? Sometimes people directly parameterize sigma inverse. Here we denote it by big lambda, right? So we call the sigma inverse or big lambda as the precision matrix or inverse Courant matrix, precision matrix. They can be used exchangeably. Any questions so far? So although it's unnecessary, but I highly recommend you to memorize the general form of a multivariate Gaussian distribution because it's so useful and so popular. So here is some intuitive looking at of this multivariate Gaussian distribution. Like suppose we're just dealing with 2D Gaussian, right? So if your covariance matrix is just identity, you can see that okay, it is essentially the density function essentially consists of circles, right? Just circles. And if it's diagonal Gaussian, meaning that the covariance is something like this, right? Like sigma 1 square, sigma 2 square, and so on. And the off diagonal parts are simply 0. Then you still see a ellipsis, but it's in parallel to the x-axis and the y-axis. Okay? But here and here are different because different. This might correspond to sigma 1 square, this might correspond to sigma 2 square. So it corresponds to different variance along different axes. Right? But in general, if your covariance is dense, meaning that you have sigma 1 square, sigma 2 square, alpha 1, alpha 2, something like that. And then if you look at the contours of your density, it'll still be an ellipsis, but it won't be in parallel to x-axis and the y-axis. It will become some kind of inclined ellipsis. So there is one key fact about multivariate Gaussian is that if we take expectation of x is simply mu, the mean parameter, and if you take expectation of x transpose, remember here it becomes a matrix. Right? It's a vector times a vector's transpose. Become matrix. This will be the covariance matrix plus mu times mu transpose. That's the basic property of a multivariate Gaussian distribution. And next, suppose we're giving like big N observations, like IID observations. How do we estimate the parameters of a multivariate Gaussian distribution? Namely, how do we estimate mu and how to estimate sigma? Again, we can write down the joint probability, right? So the joint probability is simply the product from each product of each probability, right? So it will be xn and mu and sigma, right? And if you take logarithm of the joint probability, it will be summation over the log probability of each observation, right? It will give you this one. So you can see that there's a summation. No, it's actually not summation. It's actually the logarithm of the determinant of the covariance matrix times n. That's reasonable because you got n examples, right? And in the exponential term, because you take a logarithm, your exponential just disappears, right? You're gonna summation. You're gonna do a sum over the quadratic terms across all the training examples. This is the form of the log likelihood. And we'll see that actually, as long as you know these two statistics, you can estimate your mu and sigma. You don't need to memorize all x's explicitly. That's why we call them sufficient statistics. So what do sufficient statistics mean? It means that you just need to use sufficient statistics to store the data. You don't need to explicitly store the whole data. You just need to store the sufficient statistics and use sufficient statistics to give the estimate of the parameters mu and sigma. Yes, means that if you know the summation of all x's, you know the summation of all x and x and transpose, they are enough to tell you what's the maximum likelihood estimate of mu and what's maximum likelihood of sigma, the coarse matrix. Yeah, we'll see it in a minute, right? But I just want to make sure everyone I just want to make sure we're on the same page. Does it make sense? Any question so far? Okay, so now let us do the maximum likelihood estimation, right? So we have derived that this is a log likelihood, right? So if you want to do the maximum likelihood estimation, as we mentioned, right, we just take the gradient. With respect to mu, with respect to the covariance matrix sigma, set them to be 0, so we can solve mu and the sigma. Right? So we can first take a look at the gradient with respect to mu. Okay? So this first, the two terms are constant to mu, right? The only terms that are related to mu are the summation of this quadratic forms, right? So we just take. Sorry. We just take the gradient over H summon here, and it will give you sigma inverse xn minus mu. And of course, you need to go over the summation, right? So if you set the gradient to be 0, that means you're going to set this summation to be 0. I'm not going to show how we can take the gradient to arrive here, right? I believe after homework 0, everyone is able to do that. But when we look at this, right, when we solve this, right, when we set this equation to be 0, we can immediately get our estimation, MLE estimation of mu, will simply the average of all the observed examples, x1 to x bigger. Okay. Does it make sense? Right? So it's very obvious, right? Because sigma inverse, although you don't know that, but you can view it as a positive definite constant, right? You can just throw it out, right? Then the remaining will be just solving this one to be 0, right? And the mu must be the average of all summation of x's. Right? Any question? Everyone's comfortable, right? Yeah, let me know if you feel anything strange or awkward. Just let me know. Okay, so sorry. So once we get the maximum likelihood situation mu, now let us talk about how to get the maximum likelihood estimation with sigma, right? So and then we just take gradient with respect to the covariance matrix sigma, and this one, I believe everyone has practiced this before, right? We take the gradient of this, it will be trace sigma inverse d sigma, right? This one is a little bit tedious because if you take the derivative of sigma inverse, it will give minus sigma inverse d sigma and sigma inverse, right? And use the trace operations to rotate the terms and merge them together. Eventually, you'll get this form. Again, I'm not gonna derive every detail for this. I believe everyone is capable of doing that, right? But again, if you feel like challenging of doing this, or you didn't get how to derive that, you can come to our office hour, right? We can do it together, right? Okay. And then we can set this gradient to be 0. We can solve this to get the maximum likelihood maximum likelihood estimation of the covariance matrix sigma, right? And here we have to replace mu by its optimal value, mu ml, right? So if you solve this, it will immediately give you the maximum likelihood estimation of the covariance matrix as the average over all the training examples, where for each training example, you're going to compute the auto product of the difference between xn and maximum likelihood estimation of the mu. So basically, remember mu ml is computed by averaging all the examples, right? And then here we're gonna calculate the difference between xn and their average, and multiply with this transpose as the auto product, right? And just sum over all the training examples and take average. So here's the result. And again, you don't need to memorize this, right? You just, if you want to use that, you just look up dictionary, right? But this is a well-known result, right? So there's a very interesting observation. If you look at the maximum likelihood estimation of those parameters, mu and the covariance matrix, you'll find that they're actually not unbiased estimate. So what's the meaning for that, right? So first, we know that. Let me write down mu ml here, right? The mu ml is the average of the training inputs xn, right? And the sigma ml is average of this auto product, right? So you can see that both mu ml and sigma ml are functions of the observations x1 to x big N, right? And those x1 to x big N are random variables. So that means your estimation themselves are also random variables. Does it make sense? So a natural question will be, okay, if we further take this expectation about my estimate, will they be exactly the same as the true mean and the covariance? Right. If you take expectation of your estimate, remember the estimate is a random variable, it turns out to be exactly the same as the real mean and real covariance matrix. That means, okay, your estimate is unbiased. But if you after you take expectation, it is different from the true mean or true covariance, then it is biased estimate. So first I will ask, is maximum likelihood estimation of the mu is biased or unbiased? Why? Yes. Yes, exactly, right? If we just take a look at, this is our mu ml, right? If we just take a look at this average, right? So you know that expectation of the summation is the summation of expectation, right? Because each xn are IDs to each other, right? So it is n. This guy, right? This guy is mu, right? Just calculate mu for big N times and take average, still mu, right? So that means your maximum likelihood estimation of the mu is unbiased. But what if but what's the case for the covariance matrix estimate? The covariance the maximum likelihood estimate of the covariance matrix is unfortunately biased. So that means if you take expectation of your maximum likelihood estimation of sigma, I won't give you sigma. I will give you big N minus 1 or N sigma. This is unbiased estimate. But this unbiased estimate in most cases are acceptable. Like even in the symptotic meaning that if your n is enough, right? N goes to infinity, you know that this guy converges to 1, right? So then your maximum likelihood estimate converges to the true covariance matrix, right? But here we just need to be careful because maximum likelihood estimate does not necessarily give you an unbiased estimate every time. Okay? And maybe your homework will ask you to show why the expectation of your maximum likelihood estimate of covariance will be like this. So here, I'll give you a hint, right? I'll give you a hint. So if we take a look, the MLE estimate of the sigma of the covariance matrix will be something like this, right? Again, xn subtracted by mu ml times xn minus mu ml transpose. This is definition, right? To show that if you take expectation of this guy, it gives you n minus 1 over n sigma, right? A trick will be inside each parenthesis, right? You're gonna subtract by the true mean mu and add the true mean mu subtracted by mu ml. Then try to expand this. Okay. So you will get xn minus mu times xn minus mu transpose plus mu ml subtracted by mu ml subtracted by mu transpose plus a cross term, right? Cross term will be xn minus mu transpose mu subtracted by mu ml, right? And then you can do the summation and average over every term, each of these 3 terms, and take expectation. And you will see it's relatively straightforward to get this factor n minus 1 over n. This is a very good practice for us to understand the nature of this MLE estimation, also get familiar with those concepts, mean and covariance, because this is really, really important for us. So now that the maximum likelihood estimation is a biased estimate, if we want to get unbiased estimate, it's very simple. We just replace 1 over n by 1 over n minus 1. Then it will give you the unbiased estimate of the covariance matrix. Okay, any questions so far? Okay, next we'll proceed to another very important property about the Gaussian distribution, especially multivariate Gaussian distribution. We call it partition Gaussian. So what is partition Gaussian? Like we just mentioned our x is a vector, right? Suppose I partition this x vector into 2 subvectors. Okay. So x represented by xa and xb. So correspondingly, we can partition our mean vector mu by mu a and mu b, and the covariance matrix by the blocks, right? Sigma AA, sigma AB, sigma BA, and sigma BB. And correspondingly, when we look at the precision matrix, namely the inverse of covariance matrix, we can partition the precision matrix according to A and B as well. So we got lambda AA, lambda AB, lambda BA, and lambda BB. One question is, how can we compute the conditional distribution of XA conditional on XB? Will anyone tell me what's this? what kind of distribution will be for this conditional. Anyone give me a guess? What? UA? I mean, I just want to ask, what kind of distribution do you like to leave for this conditional X equal X? Yes, exactly. Still Gaussian distribution. And this distribution is called a conditional Gaussian distribution. Right? So next, we're going to show how we're going to derive this conditional Gaussian distribution, especially what does it mean and coerce for this conditional Gaussian distribution. And by introducing this procedure that how we derive this conditional Gaussian distribution, we're going to learn or master the so-called completing square trick. And this is very, very useful. So first, if we look at the general form for multivariate Gaussian distribution, right? So if we look at the exponential term, right, we just look at the power, right, like the exponent, right? So note that it actually is a quadratic term, right? And if we expand this quadratic term, we found that it can be written as two terms related to x plus some constant. Right? And one term is quadratic to x, right? X transpose sigma inverse x. The other term is linear to x. So the x transpose sigma inverse mu, right? So the second term you can view as a linear function of x because it's a dot product between x and another vector. And the second vector is just sigma inverse mu, right? And the first term is just a quadratic term, right? And the matrix in this quadratic term is just inverse Born's matrix. So this tells us that, okay, if you can write down the probability density as in the form of exponential form, an exponent, if it contains just two terms related to x, one is quadratic term, one is linear term, plus the matrix in this quadratic term is positive definite, then it must be a Gaussian distribution, right? Because this term will always be able to written in this form, right? And if you have this form in the exponent of your exponential, right? You know that if you just normalize it, it will give you this 2 pi determinant of 2 pi sigma to the half, right? As the normalization constant. Then you give rise to a multivariate Gaussian distribution, right? That's the observation. That's what we can observe from the general multivariate Gaussian distribution. Does it make sense? Right. Any question regarding that? Because the general Gaussian distribution follow this form, right? 2 pi sigma half, right? E to the power minus 2 x minus mu transpose sigma inverse x minus mu, right? So if we do some simplification, right? Look at this here, right? You see that all terms in exponential, in exponent, right, relate to x, just the quadratic term and the linear term. And the other words, like if you think it in the opposite direction, right? If you can write down the density for any third variable, y, right? And if this probability density proportional to some exponential form, right? And has the form that in exponent that is one quadratic term and one linear term. We know that it must correspond to Gaussian. Does it make sense? Right? What we need to do is just extract the matrices and also the vector in the quadratic and linear terms respectively, match them back to the mean and the covariance. That's so-called completing the square trick. Any question? This is a cat here. Then the remaining piece is just a little bit tedious, and we're gonna proceed in a minute. But I do want you to get this cat here. Any question? Everyone comfortable with this? Okay. So this is like what we have learned, maybe middle school, high school, like, but it's not matrix and vector form. It's just a scalar form, right? You got say ax squared plus bx, right? You're gonna complete as something like ax minus c squared, something like that, right? That's why it's called completing the square trick. Right? But the only difference is that okay, now we're dealing with matrices and vectors. Okay, so now let us look at the partition case, right? So we're talking about what is the conditional distribution of xa given xb, right? So we know that x and b jointly follow a Gaussian distribution. If we look at the exponent, right, in an exponential of their joint density, we can decompose this term in terms of their partitions, right? So we know that x minus mu can be written as xa minus mu a, xb minus mu b transpose with sigma, and then xa minus mu a, xb minus mu b, right? And here, because sigma inverse, right? To be convenient, we just use its precision matrix. That means for the precision matrix, we can also partition the precision matrix, right? So they will give you lambda AA, lambda AB, lambda BA, lambda BB, right? And this one will be XA minus mu A, XB minus mu B, right? And this transpose can be further written as XA minus mu A transpose XB minus mu B transpose. Right. So now the partitioned version of this quadratic form can be written in this way, right? And then we just expand them, right? We just expand them. We got 4 terms. XA minus mu A transpose sigma AA, not sigma, lambda AA, and then XA minus mu A, right? This is the first term. And XA minus mu A, and lambda AB and XB minus mu B, the second term, right? And third term will be XB minus mu B transpose, and then lambda BA and XA minus mu A, right? And the fourth one is this one, and this one, right? So you can expand them in 4 terms, right? The reason we do this partition is that because we're conditioning on XB, right? So that means from the view of XA, XB is actually considered as constant because we're conditioned on XB, right? So we're gonna look at those all those terms that only relate to XA or that only involves XA, right? And if you look at all those terms, right, that only involve XA, we'll find okay. First, we got a quadratic term regarding XA, which is XA transpose lambda AA XA. It can be found in here, right? It's we can directly observe that because XA transpose lambda AA and XA here, right? I mean, all the other terms, there won't be any quadratic term related to XA. Okay, we can take a look at it. And similarly, if we can look at the lambda AA, right? So imagine that for our conditional Gaussian distribution, we still need to match the covariance matrix and also the mean vector, right? And the covariance matrix, its inverse corresponds to the matrix in the covariance in the quadratic term that relate to XA. So we know that, okay, the lambda AA will be the inverse of the conditional covariance matrix A given B. Right, and let's look at the second term, right? If we look at other terms that relate to XA, you'll find that they are all linear with XA, right? It's just XA transpose with some other vectors, right? If we just merge them together, you will get this, right? So we can find them from, like, you see that XA transpose and lambda AA times UA here, right? And also XA transpose with this whole thing, whole guy, right? And you just merge them together, you get a linear term for XA. So now we can see that besides this quadratic term related to XA and this linear term related to XA, all the other terms are constant to XA. You don't find any other terms related to XA. All the other terms are constant because they only involve XB. Right? There won't be like how the terms about XA, like a third order term like XA transpose XA times XA again. There won't be any other terms like that. Does it make sense? This is what we can observe from this expansion. No, it's two subvectors. Two subvectors. Yeah, like, so suppose this is x1 to x4, x5 to x10, right? I can pick this part as my xa and this part to be my xb. So it's a whole vector of your x. We partition them into two subvectors. One is xa vector, one is xb vector. Any other question? And then we look at, because when we partition x into xa and xb, and correspondingly we can partition mu into mu a and mu b, and also the inverse covariance matrix into like blocks, right? And then we just write down the exponent of their joint density in terms of their partitions. The reason of doing so is that we want to find out which terms only involve XA and which terms have nothing to do with XA. Because I want to look at what is the condition distribution of XA given XB, right? You know, if the terms doesn't contain XA, only contain XB, it's constant to XA. And from our observation, we find that, okay, there are only two terms related to XA. One is the quadratic term in this form. The other is a linear term in this form, right? And as we just mentioned, right? If you can write down the density for any variable has some exponential form, and its exponent contains only two terms that involve XA. One is quadratic term, one is linear term. That means this must follow a Gaussian distribution, right? And then we can conclude that first, okay, this conditional Gaussian distribution, that means given XB or XB is viewed as a constant, the distribution of XA is still a Gaussian distribution. And second, from what is inside of these two terms, we can match what is conditional mean and what is conditional covariance matrix for X for this conditional distribution. Does it make sense? Right. So from the linear term, right, we see that it is this guy who does dot product with XA, right? If we map to a general Gaussian distribution, we know that if we expand the general Gaussian distribution, right? In the linear term, we know that it is sigma inverse mu who does dot product with X. So that means this guy must correspond to the conditional covariance inverse conditional mean, right? As we just mentioned, right? And we know that from quadratic term, this guy corresponds to the conditional covariance. This something we have already known. We know that this guy is a lambda AA, right? It's a log of the precision matrix, right? So this one is inverse of the conditional covariance matrix. Then from this two mapping relationship, we can immediately get to the conditional mean. Okay. Remember, the sigma A given B inverse times this is this guy, right? It's just copy from here, right? Now you want to get mu, you just multiply sigma A given B on both sides, right? That's where you get here, and you do some simplification, you get the conditional mean. Just mu of A subtracted by this big lambda AA inverse lambda AB and XB minus mu B. I mean, you don't need to like exactly derive how this is get here. I just want everyone to follow the key idea, because that the details you can just practice or derive it by yourself after class. Any question regarding this whole trick? Everyone's comfortable? Is everyone comfortable? Or is this too simple? Yeah, there you go.
Going back to finding the NXT
How do we get what? Mu? Okay, so we look at linear term here, right? After we merging those terms, it's kind of tedious job. We get that, okay, the linear term will be XA transpose with this guy, right? And now, if we look at the general form of the Gaussian distribution, we know in its exponent, it has a quadratic term, it has a linear term, and the vector in the linear term will be the inverse of the covariance times mu, right? And this must match the guy you just merged, you just got. Yeah. Because this is just quadratic term. We just consider two terms, right? One is quadratic term, constant, which is constant, mu. Yes, the constant term, we just throw them out because it doesn't contain XA at all. It's just constant. So what we care about is just, okay, which term is quadratic to XA, which term is linear to XA. And then we just do the match. Any other question? Okay. So now, the remaining thing is that, okay, how do we get the precision matrix, right? We know that big lambda is sigma inverse, right? And here we actually, if we want to get a conditional mean and we want to get conditional covariance, we actually need to know what is the loss inside this precision matrix. So the last step is to leverage the, okay, here's what we get so far, right? The last step is we're going to leverage the so-called block matrix inverse form. Right? So because from our derivation, right, from our completing the square trick, we know that the conditional mean will be this guy, right? Lambda AA inverse, and this conditional covariance, the conditional mean will be mu A subtracted by this lambda A inverse, lambda AB, and XB minus mu B, right? So that means you must need to know the form of lambda AA and lambda AB. Right? So here is the general form of this block matrix inverse. Okay? If you got a matrix that can be partitioned as A, B, C, D, and it's a invertible matrix, right? And then you do the inverse, and you partition them according to the exact same dimension with A, B, and C, D. This is where each blocks should be look like. And then you just apply this. You will get what is lambda AA and lambda AB. And we substitute into our derived conditional mean and covariance. That's where we get our final version of the conditional mean and the conditional covariance. And this one is something I memorized for years. And is completely represented by the full mean and the full covariance matrix. Right? What you need to do is just the partition the full covariance matrix. You get conditional mean and conditional covariance matrix. Any questions so far? I know this is okay. Yeah, that's a very good question, because we haven't reached to the particular of specific model yet. Because if you're doing some Gaussian precise distribution, some Gaussian precise modeling or Bayesian optimization modeling, you can imagine part of the observation, the whole observation as part of them, and the things you want to predict is another part of it. And what you need to do is you want to compute the conditional distribution. That means conditional, you observe data. How do you calculate, predict the distribution of the things you are interested in? That's why we want to use this conditional variable distribution. It's actually very important for non-parametric, Bayesian non-parametric function estimations. But again, you are not required to memorize those formula, and also you do not need to memorize what this block matrix for. I'm not able to memorize it as well. But I do want everyone to understand how we can use the so-called completing square trick to derive this. Okay. So I highly recommend everyone to follow this procedure to derive it. It's a little bit tedious, but it's not hard. And as a practice, we'll have some homework assignment ask you to show that if you have this multivariate Gaussian distribution, and then if you want to derive the margin distribution of a particle like CXA, you can derive the mean will be the mu A, and covariance will be sigma A. You can use the same trick to get to that point. Okay, and sorry for being late, and let us continue on Thursday.